Before I get started, it's really exciting that there is an industry perspective on the problem also, as we witnessed in this in the morning's keynote. And we love to see this happening because it's a very important problem, and the solution we saw is also very meaningful. So we have been working also on this problem. If you are if you continue to be interested after the talks end, there will be a slide pointing at our two published works. We published a vision paper in the EDBT conference last March and a vision paper in VLDB conference last August. So feel free to check them out. Now in this presentation, I will cover the motivation for this work, so how this work originated and what it is about at a high level. And then Adil will take the floor and talk about our programming model and the runtime. And we'll finish the presentation with research direction, so what is the vision for this work. So before Adil kicks me off stage to talk about the ninja stuff, I would like us to focus on web applications, and more specifically about web applications sharing two characteristics. One, they are event-driven in the sense that they react to some external event, like a user interaction or a message from some sensor or other computer. And two, they are stateful. They record some state regarding their services, regarding their users, etc. And the world is full of these applications. I've just picked some examples that we use every day, just to see our dependence on those. They are of real value to us, not in a strict monetary sense, but I got your attention. So we have established that this is an important class of applications. On the other side of the spectrum, the teams developing these applications face difficult challenges on two fronts, on the operations front and on the programming model front. On the operations front, even if these applications are hosted in the cloud, they have to deal with a number of operation aspects. Just to name a couple, so debugging is still done by logs, and in most occasions, and configuration, well, in recent architecture styles like microservices, which have many moving parts, it's really difficult to get right. And the list of aspects grows longer if we consider scaling applications that are stateful and tolerating failures at the same time ensuring they remain in a consistent state. On the programming model front, it is many times the case that developers have to write lengthy code in order to deal with timeouts and failures, and especially in microservices, they have to do transaction processing by hand, which really sucks, right? So this is the situation, and you can note that none of these aspects is part of the core task that the development team has to do, so develop the application, right? And it shouldn't be this way. So think of a data scientist having developed a machine learning model and wants to run this model in production. She couldn't care less how it's going to run or where it's going to run. However, she has to figure this out. Fortunately, the cloud is here to help. It's moving from renting machines and renting platforms and renting software execution space to a managed service model, which offers back-end infrastructure management as a service, letting developers deploy their code. Just that. This has been termed serverless. And there is a more specific offering in production by major cloud providers called function as a service. What this involves is a programming model based on functions, where developers can just deploy their functions on the cloud, and then the users can call these functions with a specific input. On the cloud side, the cloud spawns a container, deploys there the function, passes the input gets processed, and the output is forwarded back to the user. So this seems really cool. It's helping a lot in the direction we wanted to, so in the direction of supporting stateful event-driven applications by providing them a managed backend for their operations, and a programming model with a meaningful abstraction based on functions. So imagine that, as Stefan said in the morning, we also perceive this the same way, that you can build stateful applications using functions as building blocks. This sounds really nice. But let's take a closer look at this setting. So in the example I mentioned before, I made no reference to state, right? So there is just input and the function, and gets processed and produces some output. If a function has state, then in the current FaaS offerings, it has to read that state, its current state, when the function is deployed from cloud storage, which is network attached, and it has to write this storage again at its termination. Now, this round trip time is big. It's creating latency, so it's making the processing from compute intensive to I/O intensive, and this design is not meant to support that. What is more, in order to build these stateful applications based on functions, there has to be natural function interaction and coordination. So function has to be able to call another function. Instead, what happens in current FaaS offerings is that they use two different abstractions. One, where you can define your function code, and another, which is most of the times called an orchestrator, where you define the order of the codes that are going to happen and the execution semantics, so whether they will be synchronous or asynchronous. And this is also how coordination happens. So it just doesn't feel right to have two different abstractions in order to write your application. So let's recap a bit what we have talked so far. We have stateful event-driven applications. They are an important class. They need our help and support in terms of operations and programming model. We have the cloud chipping in with a backend as a service and a meaningful programming model. However, it's not meant for stateful functions because of natural design constraints in how it manages state as an external entity and not as a first-class citizen, as it should be. And it doesn't support natural function interaction and coordination. But then if not fast, then what? Well, let's take a step back and consider how we would build stateful event-driven applications nowadays, for instance, like microservices. The easiest implementation would be to have so I'm using a typical minimal e-commerce application with order stocks and payments. So each of these would be a different service calling each other through REST calls, and there would be a single database with which each service would communicate through RPC calls. In this design, services are stateless, and the database is doing the heavy lifting. I'm not going to fully explore the designs. I'm just going to make some points about the strengths and weaknesses of each. So the main drawback of this design is the database layer, because the communication cost between each service and the database is high. In order to improve on this situation, we can separate the database into different states and push each state to the service that it belongs to. Then we have optimized the communication cost between services and the database. Services are now stateful, which is good. And the drawback here is that we haven't made progress on the communication cost between the services. There are still REST calls, and it's not really obvious how to scale this out. To remedy this situation, we can apply the event sourcing pattern by interleaving an event log between the services. Now the services become reactive because one service can push messages to another, and another service can pull that message at its convenience. The event log has also some really nice properties in that it can provide time travel debugging and auditing. Okay, yes, and because it persistently stores messages, we can recover from failures by replaying messages and rebuilding the state. Now, the drawbacks here is that we haven't really made progress on the communication cost between services. It's still REST calls. And the best consistency level we can get out of this design is eventual. However, this design is scalable. We can sort the state by some key and use the same key to route the messages from the event log to the corresponding service instance. That's good. The drawback here, one drawback here, since I'm referencing drawbacks, is that we have multiple subsystems to manage, like checkpointing, logging, reshuffling of state, scaling in and out. But the question here is, can we do better? Does this figure remind you of anything? A zebra, perhaps? No? If you can't see a zebra, then go talk to someone, it may help. But if we can perceive this topology, this design, as a data flow graph, then it becomes obvious that we can use a stream processing system to deploy, run, and manage this application and an arbitrary event-driven stateful application. Why? Because first, current stream processing systems have comprehensive state management. They can maintain consistent snapshots of state through periodic checkpointing, thereby guaranteeing exactly once processing of messages. Second, through their uncoordinated processing model, they can sustain high throughput and low latency, and because they have persistent FIFO channels, they can guarantee message delivery. And third, because state is local to each operator and it's sharded, we can build on top of that, we can scale operators in and out. Combine this with a persistent input queue like Kafka, and you have time travel debugging. So with comprehensive state management, you get a nice foundation to build on top of that scalability and fault tolerance. Okay, that covers quite a few of the operation aspects that are open for event-driven stateful applications, but what about the programming model? Well, that's okay. We can have the cake and eat it too, because we can use functions as the basic, as the one and only programming abstraction to write code. So if you can think of this as a Flink topology, then we can deploy stateful functions as operators on the data flow graph. Each operator hosts, as we call it, a function namespace, which consists of functions that share the same state. State is local to each operator, and it's sharded, and it can scale. Then services can call other services through Flink's usual communication channel. So to conclude the motivation part, we argue that data flow graphs can serve as a scalable backend for deploying, running, and managing event-driven stateful applications like microservices and cloud applications based on stateful functions. And with this, I pass the token to Adil.
Hello, good morning, everyone. My name is Adil, and I work at ING. That's a global financial organization based in Amsterdam, but we operate in 40 different countries with 36 million customers we're serving at this point. So I'd like to give you a motivation from that perspective, from the perspective of software industry. So when we're building system of that scale, we need to deal with a lot of things. So the system that we're building are highly distributed in nature, and they has to scale as well. And therefore, therefore, the system that we're building, we need to think about what kind of abstraction we are using to build those systems. If you consider one such system, it actually interacts with many other systems from the platform. And these interactions are somewhat ad hoc in nature, and the building blocks that we're using, they are built with a very low-level programming model that are not law-abiding and error-prone at the same time. So when you start composing those abstractions, proving that abstraction works is quite hard challenge, and as the system evolves, reasoning about it becomes way, way difficult. And that's why at ING we're looking into how to build systems and allow developer to build it really fast, so that we can go to market really fast. And also while building those systems, we can prove that the system actually worked by compilation. And function as a service is one of those avenues that we are exploring at this point. But at its current state, function as a service proposition, with its limitation, is not meant for a modern cloud-native solutions. And that's why we claim that we can assimilate several important characteristics from a streaming data flow system to build function as a service proposition, having state management native there. And that's why we built a prototype. We call it RAW, and we presented it at VLDV this year. And just to give you an overview, what is RAW? RAW is a stateful, event-driven function as a service platform that allow a developer to deploy function without worrying about scale, without worrying about state management, and without thinking about how it would do side effect at the end. And to that end, we're using streaming data flow as its backend. So we use Flink as a runtime for the system. Let's take a look at the programming model that we use in RAW. So the main abstraction that we use in RAW is function. And when we refer to the term function, we mean the mathematical notion of total function, which is a mapping from a state called domain to another state called codomain, such that there is each element from domain has exactly one element in codomain as a mapping. So we take that as an abstraction, and we build on top of that abstraction. In RAW, we provide 3 different kind of functions, and I'm going to focus on only these 3, but we have support for the other kind of function as well. So to get started with, we have a pure function, and then we have a function where the state is managed natively by the operating model, and then we have a function that supports some kind of orchestration. So in this talk, we're going to look at these 3 different kind of function one by one. And please note that in this talk, when we talk about function and lambda, we mean the same thing. So we use these 2 terms interchangeably. And without further ado, let's take a look at what is a stateless lambda. So consider that you need to build a ping function for a service. And with Scala, you can define it with this 2 lines of code that takes ping object as an input and return as a function. So it's very basic vanilla example of a stateless function. So in order to operationalize in the context of a RAW, we need to do some minor changes. So one thing that we need to do is to leave the context. We need to use the execution context to leave the result in it. So if you think about, if you're coming from functional programming background or familiar with Scala, you can think of it as a container like future or IO, because we'll be doing some stateful operation. And this lambda is context in which this function will be operating at the end. So here we are just describing that how a function would work. Basically, we are specifying it, and at runtime, we are interpreting this function statement by statement. So given that, we could also define a stateful lambda. So the first one is a stateless lambda, but by changing the function argument and by providing a state there, we can make it a stateful lambda. So if you think about it, this ping function would like to also track that how many times a function has been pinged or a service has been pinged. So we want to keep a state. In this context, this state here is basically a domain object, the application that you're developing, and that just extends from this managed state. So that's the only thing that you need to do to indicate that you want to manage this state by row. And let's take a look at it, how we can define this kind of stateful function. So here we are saying that we want to define a function. We want to respond with a pong message. And note that we are doing context.persist. So that's the directive that we're using to let the backend know what to do with this response. I'm going to come back to this context.persist in a later part of the presentation and explain in a bit detail that how it works. But first, let's take a look at another concept of RAW. This is called function namespace. If we want to operationalize any function, it has to be associated with a function namespace. We can think of it as a bounded context. You can think of it as a service, which has A, B, C as a different endpoints and co-located in the same namespace. So in this example, we have the function, stateful function ping, and ping defined in a function descriptor, and function namespace manages those function descriptions. But not only that, it also manages a state. So it provides a managed state for the function enclosed in that function namespaces. So in this situation, lambda1, lambda2, lambda n, they operate on a managed state provided by function namespace. And the way we define it in the context of ping, we just specify a type and point it to this ping counter that we want to use in that function namespace. We also can initialize it with the initial value. That ping counter, when the function namespace gets materialized, it will assign this initial value to that ping to the ping counter. And as we're executing any stateful function, what does it do? It actually provides the state as read-only view to that function. So the function gets a state from the runtime that is a read-only view to the state. So recall this stateful ping function that we had. Each time we're calling this function, the runtime and function namespace provide this ping counter. That is basically the local view of the state for that function. And this is a read-only view. So anything that you do on that state argument will not have any impact. But then we're specifying a couple of things here. We're saying that, hey, persist with this response time. And whenever there is this kind of persist directive, in the backend, the way it's being interpreted is that there is an event raised, and the runtime asks this onPersist event handler to do something about it. So this event handler, if you're familiar with Scala, is basically a partial function that takes a function response and state and return a new state from that operation. So the backend gets this new state, and then it starts doing something with that new state. It actually persisted in a map state and persisted with rockcb somehow. So that's the concern of backend. So in this programming model, we are not thinking about how it will be done. It's just that we are raising event and function namespaces. onPersist gets called, and it is the responsibility of function namespace how to converge it to one state and persist it. It just said that, okay, I had an old state, and this is the new state, I'm done. Do something with it. But in some cases, probably you don't want to do anything with it, and that's the second case statement there. So basically, any unknown event raised in the system, you might just ignore it and not do anything about the state. So it's kind of using some event-driven approach on handling changes on state. But this state is managed at the function namespace level. Each time one of those gets operated, the read-only view passes into those functions, and then it specifies how to modify that state, and function namespace do the right operation. And putting it all together within these 10 lines of code, we have a function, a stateful function that can run in a distributed way on top of a streaming data flow. How? That is something we are going to see in this part of the presentation. So what's the execution semantics of row? So we strongly believe that we could use streaming data flow. What Marius was mentioning, there are several interesting properties of a streaming data flow that we can use to build stateful function as a service proposition. And this is the paper that Marius was referring, something that EU and Asterios has published like beginning of this year. So with that claim, what we did, given a high-level definition of function namespace, we have a compiler that compiles down to the data flow graph. And not only that, those function descriptions are also expressed declaratively as a free algebra, if you're familiar with it. Otherwise, you can think of it as an abstract syntax tree. And there is an interpreter in the backend that's actually interpreting those during the runtime. So the data flow graph currently looks like this, that every function namespace has a request queue and a response queue. So each time a function namespace has to be executed, it actually sends a request to the request queue, and then the response is ended up in the response queue. Not only that, it actually can recursively call a function, meaning it can be calling a function multiple times recursively. So from a system engineering perspective, we do have several other components in row, we have a gateway that acts as a function discovery, and a CLI by which you can deploy a function. So basically, if you have a function namespace and you want to deploy it in the system, from the CLI, you can simply deploy it via gateway and also as a Flink job running. So this whole system takes care of lifecycle management of function namespaces as well. If we recall this previous example of ping service FN that has a stateful function called spingfn, we can use the CLI to deploy it and also execute it and undeploy it as well. So as I was mentioning, that it has this full lifecycle management, so you can deploy any function namespaces. I'm going to give you a live demo with a real-life example in the later part of the demo. The last concept that I would like to cover today is the orchestrating lambda. So basically, we have these functions. Now we need to somehow start composing those functions. And in order to support that, we have this orchestrator lambda, by which you can start composing smaller function and come up with a bigger function. So let's consider we have an order service, and in order to accept the order, first it needs to check that if a particular user has sufficient balance. If the particular user has a sufficient balance, or the amount, all the products that's in the shopping bag are in the stock service. It gets those responses back, and then it does something about it. If they get positive response from these two systems, it actually either accepts it or rejects it, depending on the response. So we have this kind of monadic comprehension. For comprehension, in the first call, we're calling payment function with a reserve cadet. So which is defined as follows. It basically checks if a particular user has sufficient balance. If the particular user has sufficient balance, it actually accepts it. It says that, OK, payment request successful. Otherwise, it says payment request fail. So in the previous example, it calls that function, and it also persists some result out of it. And similarly, it also calls this stock function, prepare order, to check if all the elements in the shopping bag are in the system. And based on that, it actually either accepts the order, otherwise rejects it. So with this kind of orchestrating function, we can start composing multiple dependent functions together with a monadic for comprehension. But we could also support the applicative way of programming as well, where you could run these two parallelly, because at the end, these are all free monad and free applicative as well. You can start running it in parallel. So recall, we had this data flow graph. I'm going to briefly explain that how this call thing works. So basically, we have a descriptions, and as soon as we get this call FN description, what happens that we suspend the current operation. We emit the event in the response queue the request queue of that particular namespace, and we wait for a particular event to come back with the result. So as the result comes in, we resume that operation, and we continue. So that's how this callback mechanism has been implemented in Row. And we basically has a callback monad that does this whole thing for us. So let's see it in action. So we have these three different function namespace. And so basically, we are running the gateway when we are also deployed two of those function namespaces, the payment and the stock. And would like to, can you see it at the beginning? Yes. So we can deploy a namespace, this order FN, simply by running this. The first thing it does, it actually creates the Kafka topic, create a Flink job, and deploy it in the platform. And then we can run this command called row list, to see all the functions that are available in the platform. So for instance, we can execute a function called payment function and initialize the balance of a particular user called E1 with 1,000 euros. Then if we run the order function with, let's say, 1 euros or something, the order is approved. But if we increase the amount to 10,000, as you can see that the order has been rejected because the user doesn't have sufficient balance. So this is all happening in the background with the data flow graph that we have. So getting back to the presentation, let's talk about performance. So we did a lot of benchmark. Actually, Pedro did a lot of benchmark on the system. And if you are interested, we can give you access to those benchmarks just to see that, just to show you how it's performing. But what we found out, for a simple example, that it's actually linearly scalable, and the latency is at less than 0.07 seconds for each function execution. Yes? So the key takeaway, at least for me, that the current function as a service has couple of shortcomings, and the two key shortcomings that we have addressed in this prototype is one, that we allow function to compose with each other, and state is the first-class citizen in this programming model. But in essence, Rho provides an event-driven programming model where the state is distributed. And instead of the data shipping architecture, we are proposing to co-locate data with code so that the code and the state that it's operating with are on the same node. And also we provide abstraction that are correct by construction, meaning that what I mean by that is that on a small granular level with code and data, you can see those abstraction works and you're done with it and you can ship it and run it in a distributed environment, and it will simply work because these abstractions are law abiding, so you could run 1,000 tests and it should work. So what next? We are looking into a different direction on this research project. Like one of the interesting things that we have to deal with is get rid of this Kafka queue in between of the data flow graph so that we can have pure data flow graph. And I understand that we do have quite some improvement with respect to the iteration support, so we can use it to refactor now so that these Kafka queues are no longer there in the data flow graph. And we are working on transactionality. We do have some basic naive implementation of compensating transactions, but yeah, we are working on it. We need to think about how to version these namespaces. We are still thinking about it. So let's say that you want to upload a new namespace via the CLI. What's going to happen to the old one? And ad hoc querying support. Now the state is sharded. How can we effectively query those sharded state? So that's one of the interesting avenue with respect to the research area. And we'd like to provide the end user with a time travel debugging so that they can go back and see what happened given that there's a problem with their code. So as you can see that we only scratched the surface of this problem domain. And we need your contribution. So if you want to participate in this project, just get in touch with us. And definitely we need more help. I'd like to thank you all to be here today on behalf of the team. And Asterios forced me to put that slide as a shameless plug from him, actually. He started this course called Damming Big Data Streams Real-Time Data Processing at Scale. So if you want to know more about streaming, or if you want to make him happy, just subscribe. He will see that, okay, there's a spike on the subscription list. Yes? So if you have any question, before we go there, I'd like to ask Pedro to join and Marius to join as well. And if you have any difficult question, it's Pedro who's going to. He has a very interesting motivation to come to Flink Forward. Yeah, right, Pedro. Let's. Yes.
Can you go back to the slide? I don't know who I'm asking. Can you go back to the slide with the 4 comprehension? Thanks so much. Maybe you didn't get it, but I have 2 questions on that. So the call function is synchronous, number 1. Number 2,
yes.
That is like a transaction, distributed transaction on different functions, right? What if I fail in between?
Yes. So your first question is if those calls are sequential.
Yeah, because I get P and I say persist P.
Yes, those calls. So in this situation, we are encoding it in a monadic way. So in the monadic way, you can encode the dependent computation. But I see that these two can be done in parallel. And that's what I didn't mention, that we can, like I mentioned briefly, that we can use applicative style of programming to have these two things run in parallel, and then when it's done with the execution, your result come back. You merge the result somehow.
Okay, so P is like a promise for something. So when context persists P, that could happen in...
No, in this context, it's sequential. It's happening one by one. In this context, it's sequential, but I'm referring to a different style of programming called applicative style, where you can actually run these two things in parallel. Okay. So basically not the persist one, the call. These two calls are not dependent on each other. So in essence, you can start executing them in parallel.
I see. And the second one is like, that seems like a distributed transaction somehow within this function and the other functions. Yes. And what if I fail in between?
Yes. So like I was mentioning, we briefly looked into compensating transaction, the Saga pattern, and one of the things we have is very naive implementation of Saga pattern, that is why we didn't show it here. Basically, you could have a compensating action for each of those actions, and then you could keep a stack and then just start actually taking action out of the stack and run those compensating action when it fails.
Yeah, so you would go for Sagas for...
We're thinking about it. That's why you can contribute, perhaps. Huh? So you saw that this is one of the things on our backlog that would like to investigate how to do transaction in this kind of context.
Okay.
So it's kind of a work in backlog, or work in progress.
I'd like to add something. Since Flink guarantees you exactly once execution, and you replay in case of failures.
Yep.
And we have a queue in between every execution. You can imagine that if something fails, you can develop a system such that it just re-executes, and when you get your answer back, you continue the computation. No. This is how Row is currently built.
Okay.
So you either fail because of domain problems, like you don't have enough credit, and if you fail by losing a machine, no. Flink will just replay it.
Yeah, I see. Okay.
Hey, great talk. Just a quick one. Is this stuff open source? Yes.
It's at GitHub. It's not yet open source, but we're planning on making it open source.
Okay, great. Because for contributing, it would help a lot to have a public GitHub. Yeah.
Cool.
Any more questions? No? Then I would like to thank you for your time and give the speakers a big round of applause.